What is life? Some says that microorganisms are life, cells are obviously life as well, and all organisms formed by collections of cells are therefore alive. Some says that fish freely roaming the oceans, birds soaring unrestrained through the sky, and humans who dominate the land are all forms of life. Trillions upon trillions of life forms on Earth together compose a vibrant, ever-renewing, and remarkably beautiful world. This inevitably leads us to ask, how did the complex and diverse species of this world come into being? And how many countless chaotic collisions did disordered atoms in the universe endure before they were lucky enough to assemble DNA and proteins, allowing life to emerge? Because this episode is relatively long, it will be presented in 3 chapters: Death from Space, Our Place in the Universe, and Gifts from the Stars. As the summer morning sun rises, the deep shadows of the Alps gradually retreat from lush green meadows nestled quietly between snow-capped peaks. Colorful wildflowers slowly open toward the sun, insects lazily dance among the blossoms only to be snatched away by swift snow finches. A marmot cautiously pokes its head out to watch a group of ibex climbing the meadow's edge, and a stoat greedily fixes its gaze on other mammals. Here, plants and animals coexist in harmony, perfectly adapted to the alpine meadow environment. Yet within these cold meadows, and every ecosystem on Earth, there are deeper, invisible forces shaping the composition, behavior, and appearance of all living things. These forces do not originate from within Earth itself, but from the distant universe. In the vast starry sky, the grasses and flower colors covering the alpine meadows depend on the sun's size and age. The appearance of wildflowers and insects in the morning is, to some extent, owed to the moon, whose presence also grants stable seasonal cycles and the advance and retreat of glaciers. The gentle streams that sustain meadow life benefit from the specific arrangement of planets in the solar system, and even the breathable air at these high altitudes relies on the unique conditions present during Earth's formation. In fact, the mammals and birds coexisting here exist only because certain life forms that once dominated Earth went extinct due to extraterrestrial catastrophes. Some of these disasters are familiar, such as the blazing meteor that fell from the sky and destroyed entire ecosystems, while others were quieter and more concealed, yet equally profound. Ultimately, whether in the alpine meadows or anywhere else, life depends on our unique position in time and deep within the universe. Evolution is the process by which life changes to adapt to its environment, but over Earth's 4.5 billion year history, cosmic forces from beyond our planet have guided the direction of evolution through creation, adaptation, and destruction. Without both the cruelty and kindness of the universe, it is almost certain that we would not be here at all. On another Earth in a parallel universe, cities are not jungles of skyscrapers but vast natural forests, where arboreal dinosaurs carefully tend their eggs, newly hatched young leap nimbly among branches, and older reptiles bask lazily in the sun, their eyes fixed on the sky. Above the canopy, there is no cheerful birdsong, but the heavy wing beats and piercing cries of pterosaurs, slowly circling on thermal currents before diving like blades. The shadows of enormous solitary predators briefly blot out the sunlight, casting fields of death below. Beneath wind-rippled waters, groups of plesiosaurs gather to hunt sturgeon and turtle-like fish, while in deep bays, massive mosasaurs in mating season swim in groups, singing to one another in low tones that echo through the water as a low-frequency symphony. In this reptile-dominated world, some birds, fish, and small mammals still exist, but they live constrained and humble lives, struggling along the margins of every habitat. The fearsome giant lizards, descendants of Tyrannosaurus rex, continue to occupy the top of the food chain on land, in the sky, and in the water. This radically different future of life on Earth stems from an event tens of millions of years ago, or more precisely, from the absence of a celestial event, 66 million years ago. In this parallel universe, an asteroid skimmed past Earth at a speed of 72,000 kilometers per hour. For the giant dinosaurs that once roamed the continents, this asteroid looked like nothing more than a fast-moving star. They continued living their reptilian lives, never knowing they had narrowly brushed past extinction. Of course, in our universe, events did not unfold this way. By the late Cretaceous, Earth was almost entirely ruled by dinosaurs, which, along with their close relatives, had thrived for nearly 180 million years. Other animal groups existed, but largely in the dinosaur's shadow. In fact, during the late Cretaceous, bird lineages had already diversified, with primitive birds coexisting alongside some early modern birds, while small, primitive mammals scurried for survival beneath the feet of gigantic dinosaurs. Mollusks constructed reef-like structures resembling modern coral reefs, attracting coral fish, sharks, and crustaceans such as lobsters and crabs. Earth's ecosystems at that time were highly diverse, even though dinosaurs still occupied the dominant position. However, the late Cretaceous was not a stable period in Earth's history. As the Indian subcontinent slowly drifted toward Asia, massive volcanic activity erupted continuously. Lava and greenhouse gases poured out for roughly 2 million years, driving ecological change and evolution. Many once dominant dinosaur species began to decline, though in North America dinosaur numbers remained at their peak until the catastrophe from the stars arrived, abruptly bringing everything to a halt. In 1980, physicist Luis Alvarez and his geologist son Walter Alvarez discovered the first conclusive evidence for dinosaur extinction. While studying geological strata, they found that at the boundary between the Cretaceous and Paleogene periods, the concentration of a particular element was far higher than normal. This anomaly appeared in boundary clay layers worldwide, but was especially pronounced near Mexico. This element, iridium, is extremely rare in Earth's crust because it is siderophilic, meaning it tends to bond with iron. During Earth's formation, iridium migrated with iron toward the core, leaving the crust depleted. Therefore, when the Alvarez team detected an abnormal spike of iridium in the strata, they concluded it must have arrived after Earth's formation, precisely 66 million years ago, the critical moment marking the end of the dinosaur era. They further inferred that the iridium originated from the impact of a comet or asteroid, which, upon striking and disintegrating, spread its elements globally. The idea that such an impact caused the end of the dinosaur age is now firmly established. This city-sized asteroid formed beyond Jupiter's orbit and may have wandered through the solar system for thousands of years, circling the Sun until its path intersected with Earth's. It struck at a speed of 20 kilometers per second, slamming into the Yucatan Peninsula at a 60-degree angle from the horizon and completely disintegrating on impact. The energy released was equivalent to the explosion of more than 1 billion nuclear bombs and triggered a magnitude 10.1 earthquake, shaking the entire planet as if it were alive and having a very bad day. The blast heated the atmosphere to thousands of degrees Celsius, turning the sky blood red and igniting global wildfires. Vaporized rock filled the air, and the crust at the impact site was reshaped into a massive crater over 180 kilometers in diameter and 20 kilometers deep, surrounded by mountain rings taller than the Himalayas. The force of this collision exceeded anything Earth had experienced in billions of years. Yet what truly drove mass extinction was the long chain of aftermaths. Sulfurous gases and dust formed a global haze that blocked sunlight, plunging Earth into an impact winter lasting up to 15 years. Tropical temperatures fell to around 5 degrees Celsius. Most deadly of all was the loss of sunlight. Without it, plants could not grow, and the global food chain collapsed. Herbivores starved, followed inevitably by carnivores. After the cold and darkness came intense heat. The immense energy of the impact oxidized carbonates at the site, releasing vast amounts of carbon dioxide and triggering a greenhouse effect that lasted 100,000 years. The final outcome of this cosmic disaster was the third largest mass extinction in Earth's history. Up to 3/4 of all species vanished, including all non-avian dinosaurs, flying reptiles, and large marine reptiles. Even the ammonites, which had dominated the oceans since the early Mesozoic, were completely wiped out. On land, animals weighing more than 25 kilograms were unlikely to survive. In the end, the right to inherit Earth fell to small survivors, mammals, birds, and lizards, scraping by on detritus and dead plant matter. After the climate crisis of the early Paleogene subsided, ecosystems slowly began to recover, with flowering plants rapidly rebounding thanks to their resilient seeds and pollen. They gradually replaced the more primitive spore-reproducing gymnosperms, quickly rising to become the dominant plant group of the time. Soon after, grasses also evolved during this period and would later become key components of new ecosystems. On land, animals remained relatively small for thousands of years. In fact, birds were among the first to increase in size, although most of these early giant birds are now extinct. It was not until about 15 million years after the end of the Cretaceous that mammals larger than a small horse gradually appeared. In the oceans, aside from sea turtles and crocodilians, all marine reptiles had vanished. Fish populations were initially dominated by sharks and ray-finned fishes, but eventually bony fish replaced them, becoming the most numerous organisms in the seas. Thus, from the end of the Cretaceous to the beginning of the Paleogene, the biospheres of land, sky, and ocean all underwent one of the most dramatic transformations in history. The changes of this period shaped the living world we inhabit today, and all of it stemmed from a chance yet devastating event originating beyond Earth. However, the Cretaceous-Paleogene extinction may not have been the only extraterrestrial disaster driven by cosmic forces. Such forces have repeatedly stirred the course of evolution on Earth. In fact, deeper in the past, and perhaps from even farther reaches of the universe, a more violent event may have invisibly contributed to one of the 5 major mass extinctions in Earth's history, influencing the direction of life's evolution. The late Ordovician mass extinction occurred about 445 million years ago and was second in scale only to the Permian-Triassic extinction, making it the second largest biological crisis in Earth's history. This extinction was complex, unfolding in 2 distinct phases, and ultimately eliminated about 85% of species, 27% of families, and 57% of genera, brutally pruning the tree of life only 100 million years after the Cambrian explosion. During this time, many marine invertebrates such as trilobites, brachiopods, and graptolites, along with jawless vertebrates like conodonts, were completely wiped out. Unlike the end Cretaceous extinction, however, the late Ordovician event did not reshuffle biological classes entirely. Although many species, genera, and even whole families disappeared, each major group retained survivors that carried on their evolutionary journeys. In other words, this extinction stripped away most of the leaves and twigs of the tree of life and even chopped off a few thick branches, but the main trunk remained intact. Perhaps for this reason, the precise cause of this first major mass extinction remains unresolved. The most widely accepted explanation links the extinction to intense glaciation, followed by climate warming and widespread ocean anoxia, which together amplified its severity. Geological evidence indicates that Gondwana drifted into the Antarctic region, disrupting global circulation and developing a continental ice sheet similar to modern Antarctica. The organisms of this period were adapted to warm tropical oceans, so the sudden onset of cold proved lethal. When temperatures later rose and glaciers melted, extensive ocean anoxia followed, lasting up to 3 million years and delivering a second devastating blow to surviving species. There is no doubt that environmental conditions at the time were sufficient to cause mass extinction on a global scale. What remains unclear is what ultimately triggered the glaciation and anoxia. Many researchers believe the cause was a combination of factors. The evolution of land plants and the flourishing of phytoplankton may have drawn down large amounts of carbon dioxide, weakening the greenhouse effect. Volcanic activity may have declined abruptly, reducing the replenishment of atmospheric CO2, and the rapid uplift of new mountain ranges along with increased carbonate weathering may have further lowered CO2 levels. Together, these processes may have reduced atmospheric carbon dioxide, weakened Earth's greenhouse blanket, and dragged the planet into an ice age. Yet even this combination seems insufficient to fully explain the scale and suddenness of the glaciation. As a result, scientists have proposed more unusual hypotheses. One recent example is the discovery of a massive circular landform in southeastern Australia, whose formation age coincides with the onset of this extinction. The structure may be an impact remnant up to 520 kilometers in diameter, though whether it represents evidence of another catastrophic asteroid impact remains unconfirmed. Another equally intriguing possibility is that the extinction was not caused by an impact at all, but by intense exposure to cosmic radiation. Over the long history of the universe, massive stars end their lives in supernova explosions, releasing vast amounts of dust and radiation. What we observe through telescopes today is merely the fading afterglow of those ancient cosmic blasts. The flickering of visible light and the eruption of radiation are spectacular to observe. However, unless these outbursts occur at extremely close range, they are usually nothing more than dazzling decorations in the night sky. There is, however, one type of cosmic explosion that can cause widespread destruction even from thousands of light years away, leaving lethal effects on distant planets. These are gamma-ray bursts, first discovered by humans in the 1960s. As the name suggests, a gamma-ray burst is a brief but extremely intense release of gamma radiation, typically emitted in an extraordinarily narrow beam and lasting anywhere from less than 2 seconds to several minutes. To produce radiation of such power, these events must be unimaginably bright. Their luminosity is hundreds of times greater than that of an ordinary supernova, and at peak intensity can briefly outshine the sun by a factor of 1,000,000 trillion, an impressive feat for something that is over almost as soon as it begins. Despite decades of study, the precise origin of these powerful explosions is still not fully understood. Gamma-ray bursts are thought to arise either from the collapse and violent death of massive stars, producing a type of supernova, or from the collision of two extremely dense neutron stars. Regardless of their source, such events are exceedingly rare, occurring only a few times per million years within a single galaxy. In 2022, scientists observed the most powerful gamma-ray burst ever recorded, originating in a galaxy 2.4 billion light-years from Earth. Even at that immense distance, when its beam reached our planet, the radiation was strong enough to push satellite detectors to their maximum measurement limits. The burst produced measurable changes in Earth's atmosphere and disrupted long-wave radio communications in a manner similar to an exceptionally powerful solar flare. So far, all gamma-ray bursts we have observed have occurred outside the Milky Way, which is, from Earth's perspective, extremely fortunate. The energy involved in these events is so immense that if a gamma-ray burst within our own galaxy were aimed directly at Earth, the consequences for the atmosphere and biosphere could be catastrophic. Estimates suggest that, over an 11-year timescale, Earth could be exposed to 2 or more potentially lethal gamma-ray bursts. For this reason, some scientists have speculated that a similar event may have been responsible for the late Ordovician mass extinction. This raises a troubling question: how could such a distant cosmic explosion cause the extinction of as much as 85% of life on Earth? If a gamma-ray burst were to strike Earth directly from within about 6,000 light-years, the enormous energy released in a short time would be sufficient to completely strip away the ozone layer. The ozone layer is Earth's primary shield against harmful ultraviolet radiation from the sun and other sources. Once it is destroyed, intense ultraviolet radiation would reach the planet's surface and penetrate tens of meters into the ocean. This situation could persist for roughly 10 years, until the ozone layer gradually recovered. High-intensity ultraviolet radiation damages DNA and causes widespread biological death, with particularly severe effects on microorganisms lacking effective protection. During the first phase of the late Ordovician extinction, the pattern of species loss is consistent with sudden and lethal radiation effects. Organisms living at the surface or in shallow waters, especially plankton floating near the ocean surface, were far more severely affected than species living in deeper waters or sheltered on the seafloor. Researchers estimate that this radiation may have wiped out 20 to 60% of the world's photosynthetic plankton, triggering the collapse of food chains that depended on them. Gamma-ray bursts can also account for the sudden onset of an ice age and the subsequent mass extinction without invoking additional internal Earth processes. When high-energy gamma rays strike the atmosphere, they break ozone molecules into free oxygen atoms. These atoms then combine with atmospheric nitrogen to form nitrogen dioxide, a dark aerosol that can linger in the upper atmosphere and reflect sunlight. As a result, the amount of solar energy reaching Earth is reduced by several percent, leading to a rapid global cooling. Eventually, the nitrogen dioxide settles to the surface as nitrates, supplying nutrients to the environment and promoting the recovery of plankton. This process increases the consumption of atmospheric carbon dioxide, further enhancing global cooling and creating conditions favorable for subsequent ocean anoxia. In this way, gamma-ray bursts can explain many, perhaps even all, of the key features of the late Ordovician extinction. This hypothesis offers an elegant solution to a complex problem, but it has also sparked considerable controversy, much like the Alvarez asteroid impact hypothesis did in its early days. Unlike volcanic eruptions, glaciation, or giant asteroid impacts, however, brief and intense cosmic radiation events leave no trace in the geological record. As a result, the gamma-ray burst hypothesis is almost impossible to support with direct evidence. At present, there is no definitive proof that such an event has ever occurred, and for the foreseeable future, the idea remains speculative. In reality, the only possible evidence for the impact of gamma-ray bursts on Earth's life may be for such an event to occur again within humanity's lifetime, a possibility that is not entirely remote. Based on an estimated frequency of 2 events every 11 years, even if one occurred during the late Ordovician, we may still witness a gamma-ray burst within the Milky Way in the relatively near future. Unlike asteroid impacts, for which we might receive early warnings, gamma-ray bursts are completely unpredictable. Once we detect one, it is already too late. The destructive power of dying stars has shaped the course of life on Earth in the past, and it is almost certain to do so again in the future. The fossil record tells us that random events from space can instantly redirect the path of evolution. Yet the universe's guiding hand is not always so violent or so obvious. We will continue exploring this idea in the next episode. If you enjoy this kind of content, don't forget to follow and subscribe. See you next time.